This is 4.7 L'Hopital's. So back in chapter 2, you learned how to do limits. So as a reminder, this first one, if you plug in 0 on top and bottom, the numerator approaches 0 and the denominator approaches 0. And we said this is indeterminate. And so in this one, we actually used the squeeze theorem to find the answer. It came out to be 1. Then in this case, you plug a 2 here, and on the bottom, the top and bottom both approach 0. And again, we call this indeterminate. We don't know what it's doing. But then, if you factor the top and bottom and canceled, whoops, then you plug in 2. You get your limit. And the third one, I'm not going to do this one, but if you plug infinity on top and bottom, the top approaches infinity and the bottom approaches infinity. We also said this was indeterminate. And in this one, we divided everything by x squared on top and bottom. But then for the top, we rewrote the top as square root of x to the 4th. That way, the square roots, you can divide everything, and you would get an answer. I can tell you the answer. The top would have been 3 over, top is 3 and the bottom is 2. So these are all different techniques we had in finding these limits. So now we come to theorem 4.13. What does it say and what's going on? So we have two functions, f and g. They're differentiable on some interval I. And then in that interval, you have a point A. So basically what this is saying, if the limit of the numerator approaches 0 and the limit of the denominator approaches 0, then something special happens. So this was in an indeterminate form. So basically the top and bottom are both approaching 0. Well, L'Hopital says you can take the derivative of the top function, the derivative of the bottom function, and that limit is the same as the limit of the original function. And so that's called L'Hopital's. And that's going to make your life so much easier. We're going to do some examples. So in the first example, now I want to warn you, because people will do this. Let's see, 1 plus 1 is 2, minus 2 is 0. And they say this equals 0 over 0. Right there, that's a false statement. This is indeterminate. To say it equals 0 over 0, we learn dividing by 0 doesn't exist. By stating this, you're saying this limit does not exist because that does not exist. So that's not how you want to go about doing the L'Hopital's. So you would say the limit as x approaches 1 of the numerator equals 0. Then you take the limit of the denominator separately. So since the top and bottom both approach 0, therefore I can apply L'Hopital's. So on this one, therefore, by L'Hopital's, this equals what? You take the derivative of the top and bottom. So it's the limit as x approaches 1. The derivative of the top would be 3x squared plus 2x minus 2. And the derivative of the bottom is just 1. Now you take this limit. Couple common mistakes. Some people do quotient rule, low d high minus high d low over low squared. That's not what L'Hopital says. L'Hopital says you take the derivative of the top and you take the derivative of the bottom, not the derivative of the whole thing. Now I can plug in 1. What do I get? 5 minus 3 over 1, which is 3. So that limit would be 3. Here's another example something that we've done in the past where we would have had to done some strange form. In this case, we would have had to multiply by the conjugate. I don't know if you guys remember that. So if you plug in 1 on top, you're going to get 0. 1 on the bottom, you're going to get, I messed up on this. This is approaching 0. My apologies. Let me fix this. So this one, x is approaching 0. On top, you're going to get 0. On the bottom, you can get 0. But to show your work, you have to show the limit of the top equals 0, and the limit of the bottom equals 0. Therefore, now you can apply L'Hopital's. So you have to show the top and bottom both approach 0. Then you can rewrite this as the derivative of the top and the derivative of the bottom. Now the derivative of the top, using chain rule and all kinds of fancy stuff, you're going to get 1 over, it's actually going to be 3 over 2 square root of 9 plus 3x. And the bottom's going to be 1. Now you plug in your 0. The top's going to be 3 over 2 times 3 over 1. And I get 1/2 for that answer. Now, to show the derivative of the top, I did chain rule. You can verify that that is the derivative of that, but you just have to use chain rule and rewrite that. I have a couple more examples here. So here's the third example. So I need to take the limit of the top, and e to the 0 is 1 minus, e to the 0 is 1 minus 0 plus or minus 1. 1 minus 1 is 0. So the limit of the top is 0. If I do that to the bottom, clearly that's going to be 0. So I can apply L'Hopital's to this. So this equals, according to L'Hopital's, I can take the derivative of the top, I am my own grandpa minus 1, over 2x. Now, if I take the limit again of the top, that comes out to be 0. And the limit of the bottom, that comes out to be 0. This is again L'Hopital's. I can apply a L'Hopital's again. So according to L'Hopital's rule, I take the derivative of the top, which is e to the x, derivative of the bottom is 2. And now, I'm running out of room here, the limit as x approaches 0 of e to the x over 2 will be e to the 0 over 2, which is 1/2. And so that answer is going to be 1/2. Okay, so I had to do L'Hopital's twice. So think of it this way, if you're thinking, can I do that? What if I didn't give you this original, and I only gave you this? You would have got 0 over 0. You would have determined that's indeterminate, and you would have applied L'Hopital's, and you would have gotten that. So you can apply L'Hopital's as many times as you need to, as long as you have an indeterminate form. All right, so this example, example 4, we have to take the limit of the top and bottom. The limit x approaches 2, x cubed minus 3x squared plus 4. Well, that's going to be 8 minus 12, which is negative 4 plus 4, 0. Take the limit of the bottom. Okay, so plug in 2. That's 16. That's going to be 32, so that's negative 16. Negative 16, plug in 2 here. That's plus 28. That's going to be 12. And then plug in 2 there, minus 24. That's negative 12 plus 12. That's 0. So by L'Hopital's, we can say this equals, and take the derivative of the top and the derivative of the bottom. 3x squared minus 9x over 4x cubed minus 12x squared plus 14x minus 12. Now we plug in 2 again. So let's find the limit of the top. That's going to get us what? 4 times 3 is 12. I forgot something, didn't I? Let me double check this. Okay, so the top is 3x squared. See, I don't know how to do math. That's a 6. Now that's better. So that's going to be 12 minus 12, which is 0. You take the limit of the bottom. And let's do this. It's going to be 32. That's 4 times 12 minus 48. So 32 minus 48, that's negative 16, plus 28. Negative 16 plus 28 is going to be 12 minus 12, which is 0. So by L'Hopital's, we do this one more time. The derivative of the top is 6x minus 6. The derivative of the bottom will be 12x squared minus 24x plus 14. And now we do this, we're just going to get 3 over 7. So that's the answer. So you could do L'Hopital's twice, 3 times, 4 times, as many times as you need, as long as you have a 0 over 0. Okay, now we're going to add one other situation to L'Hopital's. So this is exactly the same, but now if the top approaches either positive or negative infinity, and the bottom approaches either positive or negative infinity, L'Hopital's also applies to this case. And so therefore, the limit of a quotient, you can take the limit and take the derivative top and bottom, and it will be the exact same limit. So all we're doing is expanding L'Hopital's rule to a situation where you have infinity over infinity instead of 0 over 0. All I have are 2 examples, and I don't know how to count because example 5. Clearly this is 6. I'll try to fix the notes that I give to you. You can actually try these yourself and see what you get. And then we can compare answers. And again, I messed up on this one. This should be infinity. I'll fix that on yours. And the next one should be pi over 2 from the left. Okay, so let's do these. So the limit as x approaches infinity, 4x cubed, 6x squared, plus 1. Clearly the top's infinity. I do the same thing to the bottom. And that's going to be 2x cubed minus 10x squared plus 3. Clearly the top's infinity. So by L'Hopital's, we're allowed to take the derivative of the top and the derivative of the bottom. The top, what are we going to get? 12x squared minus 12x. On the bottom, 6x squared minus 20x. So what do we do now? Well, I'm running out of room. Here's what I'm going to do. I'm going to move this down here and say that's equal to this limit. All right, now I take the limit again. 12x squared minus 12x. That's clearly infinity. Take the limit of the bottom. So minus 20x. And clearly that's infinity. So by L'Hopital's, we could take the derivative of the top and bottom again, which would give us 24x minus 12 over 12x minus 20. And then you take the limit of the top. Clearly that's infinity again. You take the limit of the bottom. Clearly that's infinity. Therefore, apply L'Hopital's again. The derivative of the top is 24. The derivative of the bottom is 12. That equals 2. There is my limit using L'Hopital's multiple times. In fact, I did 1, 2, 3 times in this case. All right, last example, and we will be done. So I want the limit as x approaches pi over 2 from the left of 1 plus 10x. So the tangent function is sine over cosine. So in your head, you can picture it as sine x over cosine x. Well, you know what? That's sloppy. Let me just rewrite this below. Okay, so sine of pi over 2 is going to be 1. And if you approach pi over 2, cosine of pi over 2 is approaching 0. We're approaching from numbers smaller than pi over 2. So we're approaching in the first quadrant. We're approaching pi over 2 from this side. Cosine's approaching 0 from positive numbers. So that's going to be positive infinity. Take the limit of the bottom. But I'm going to rewrite secant as 1 over cos x. The top is 1. The bottom is approaching 0 again, the same reason. Pi over 2 is right here. We're approaching from numbers smaller. So it's approaching 0 from numbers smaller than 0. That's going to get us again infinity. Sorry, it's approaching 0 from positive values. So the bottom's approaching 0 from positive numbers. So we're getting infinity over infinity, and therefore we can apply L'Hopital's. Let's see, the derivative of 1 is 0. The derivative of tangent is secant squared. And the derivative of secant is secant tangent. And one of those secants will cancel out one of those secants. And what do we have to do here? We can simplify this further. That's what we're going to do. So a little side work. Secant is 1 over cosine. And tangent is sine over cosine, which is multiplying by cosine over sine. And so that can all be replaced by 1 over sine. So this is the limit as x approaches pi over 2 from the left of 1 over sine of x. But, again, remember this is side work that we did. The top is 1. The sine of pi over 2 is 1. So the answer is going to be 1. So that is our last example, and that's it for these notes.